Before gold is ever seen, before a single flake flashes in sunlight, the Earth leaves a quieter signal. It does not glitter. It does not announce itself. It waits inside the bedrock, where pressure, time, and fracture tell a story older than any map. Most people search rivers, others chase veins. Professionals, however, begin somewhere deeper. They begin with a sign that never moves, never floods away, and never lies. Bedrock remembers everything. Across North America, some of the most consistent gold discoveries were not predicted by maps, claims, or historical records. They were predicted by a subtle change in stone, a texture, a break, a surface that behaves differently under pressure and water. This sign is rarely discussed outside professional geology, yet it has guided discoveries for more than a century. And once you understand it, maps become secondary. Gold does not choose its location randomly. It obeys physics, it obeys chemistry. But above all, it obeys structure. Deep underground, where rock once flowed instead of cracked, immense forces shaped the pathways that gold would later follow. These forces left scars in bedrock that still exist today, even after mountains eroded and rivers changed course. The first mistake most prospectors make is believing gold belongs to the river. Rivers only transport gold. They do not create it. The true decision of where gold ends up is made long before water ever touches it. That decision happens when bedrock breaks, shifts, and seals again under enormous stress. Certain bedrock surfaces develop what geologists quietly call receptive zones. These are areas where the rock's physical properties allow heavy minerals to settle, lodge, and remain trapped for geological timescales. Gold favors these zones because gold is heavy, soft, and easily deformed. When moving water loses energy, gold does not roll like gravel. It presses downward. It searches for resistance, and bedrock provides it. But not all bedrock is equal. Smooth, polished bedrock often signals past glacial movement or prolonged water abrasion. While it may look promising, it rarely holds gold for long. Gold needs interruption. It needs texture. It needs edges that break flow and create micro-pressure drops. The most valuable bedrock surfaces are those that appear damaged, fractured, and irregular. One of the most reliable signs is a specific pattern of cracking that runs against the natural slope of the rock. These fractures are not random. They are tension cracks formed when stress exceeded the rock's ability to flex. When hydrothermal fluids later pass through these same cracks, they carry dissolved minerals, including gold. Even when visible gold never formed a vein, microscopic particles remain behind, waiting. Over time, erosion removed the softer surrounding rock, exposing these fractures at the surface. Rivers later crossed them, unknowingly reactivating a trap created millions of years earlier. When water flows across such bedrock, gold behaves predictably. It sinks into the fractures and locks in place. This is why experienced prospectors pan above bedrock first, not below gravel depth. They are not searching randomly, they are reading structure. Another critical sign appears when bedrock displays alternating hardness within a small area. This often happens when different rock types were fused or altered by heat and pressure. Gold favors boundaries. When hard rock meets softer rock, water slows just enough for heavy particles to drop. Over thousands of years, this creates concentrated pockets invisible from above. Professionals recognize this immediately. They do not need a map to tell them where gold might be. The rock itself provides the information. In many American gold regions, especially those influenced by tectonic compression, bedrock surfaces show subtle folding, rather than clean breaks. These folds act like natural riffles. During high water events, gold is forced downward into the tightest curves of the fold. Once there, it rarely escapes. Floods may move lighter material away, but gold stays behind. This is why some locations produce gold consistently year after year, even after being worked repeatedly. The source is not replenishing. The trap is simply effective. Another overlooked indicator is bedrock oxidation. When iron-rich minerals within bedrock oxidize, they create rough, granular surfaces that dramatically increase gold retention. These surfaces feel different under hand and tool. They grip instead of polish. Gold adheres to them with surprising strength. Geologists pay close attention to these textures because they reveal chemical environments favorable to gold deposition. Oxidized bedrock often indicates earlier sulfide mineralization, which is closely associated with gold-bearing systems. Maps rarely show this level of detail. A geological map may tell you the general rock type. It may outline fault zones and formations, but it cannot show you how a specific bedrock surface behaves under flowing water. It cannot reveal microfractures or texture changes. Those signs must be read in person, stone by stone. This is why some of the richest placer gold areas in the United States were discovered after decades of being overlooked. The information was always there, embedded in the bedrock itself. It simply required a different way of seeing. Gold responds to gravity, resistance, and confinement. Bedrock provides all three. When the right sign appears, it predicts gold more accurately than any historical record. And once you learn to recognize it, you stop chasing gold blindly. You start predicting it. Once you begin to read bedrock as a record rather than a surface, patterns start to emerge with surprising clarity. What once appeared like random stone suddenly behaves like a map written in texture, angle, and resistance. The Earth, it turns out, has been marking gold locations all along. It simply does not mark them in ink. The most telling bedrock signs rarely appear in isolation. They combine. A fractured surface aligns with a hardness boundary. A change in texture coincides with a subtle shift in slope. When these elements converge, gold's behavior becomes almost inevitable. Water loses energy, pressure changes. Heavy particles respond instantly. Gold settles where physics demands it must. One of the strongest confirmations comes from how sediment behaves above bedrock. When coarse gravel abruptly transitions to compacted fines directly over a fractured or folded surface, it signals repeated sorting events. Flood after flood, lighter material is swept away while gold sinks deeper, driven into the same traps again and again. These zones are not accidents. They are persistent. Experienced geologists pay close attention to what sits directly on the rock. Clay layers, especially those rich in iron oxides, act like sealing membranes. Once gold passes through them during high-energy flow, it becomes extremely difficult to remove. Even aggressive floods fail to dislodge it. This is why some bedrock cracks yield gold long after surrounding areas are depleted. Another critical indicator lies in orientation. When fractures or grooves cut across the direction of water flow instead of running parallel to it, gold accumulation increases dramatically. Flowing water cannot maintain velocity across these interruptions. Microeddies form, pressure drops. Gold reacts instantly, pressing downward into the rock where movement nearly stops. This principle applies not only in rivers, but in ancient channels long buried under sediment. Even when water is no longer present, the bedrock retains its signal. Miners who understand this can predict gold locations beneath dry ground, guided by structure rather than guesswork. Heat-altered bedrock provides another powerful clue. In areas once affected by hydrothermal activity, the rock often appears bleached, hardened, or chemically altered. These zones indicate that mineral-rich fluids once passed through, depositing metals at depth. When erosion later exposed these surfaces, they became prime locations for secondary gold concentration. Gold's softness plays a crucial role here. Unlike quartz or magnetite, gold deforms under pressure. When trapped in bedrock irregularities, it flattens, molds, and locks itself into place. This is why bedrock gold often appears worn, compacted, and tightly embedded rather than loose and shiny. Its shape tells a story of how long it has remained undisturbed. Professionals do not chase sparkle. They chase confirmation. They look for repeated evidence that the environment favors gold retention. A single flake may be coincidence. A pattern is not. As these signs accumulate, confidence replaces hope. Each bedrock feature reinforces the next. Fracture leads to fold. Fold leads to texture. Texture leads to chemistry. And chemistry leads to gold. This is why relying solely on maps often leads to disappointment. Maps describe regions. Bedrock describes outcomes. One shows where gold might exist. The other shows where gold cannot escape. Understanding this difference transforms the way gold is approached. Prospecting becomes predictive rather than reactive. Every step is informed. Every decision grounded in physical reality rather than chance. And perhaps most importantly, this knowledge narrows focus. Instead of working endless ground, attention shifts to precise locations where the Earth itself has done most of the work already. Time becomes an ally rather than an enemy. Gold is patient. It waits where conditions demand it must remain. Bedrock, shaped by forces far beyond human scale, records those conditions faithfully. When you learn to read that record, you stop asking where gold might be. You start knowing where it has no choice but to be, because the most reliable gold signal was never written on a map. It was written in stone.